When dealing with material upsampling, processing each SVBRDF map independently using classical image filters, such as bilinear or Lanczos, leads to strong aliasing and ringing, as seen in these examples. We present a method for SVBRDF super resolution which provides sharper and more detailed maps. This is visible in these zoomed-in insets. For traditional RGB image super resolution, machine learning techniques have proved to surpass standard signal processing filters such as bilinear, bicubic, or Lanczos interpolation. However, they are optimized to upsample natural images, not SVBRDFs. Direct RGB super resolution of SVBRDF maps using such ML-based upsamplers is not viable, because material maps differ in nature, geometric constraints, and statistics from RGB photographs. Besides, all maps contribute in a very different manner to and have a different impact on the final shading. We experimentally find that RGB upsamplers provide pleasing results when applied on rendered materials, such as this 128 by 128 input. Here are the results of radiance upsampling by 3 different approaches. To leverage such upsampled radiance, a simple per-pixel approach consists in rendering a low-resolution SVBRDF under multiple lighting conditions, and upsampling the results using a given RGB upsampler. Then, the input SVBRDF is upsampled bilinearly to provide the optimized variables, used along with a differentiable pipeline. These SVBRDF texels are optimized by backpropagation using a rendering loss between its renderings and their upsampled counterparts. Here is a result compared with simple per-channel bilinear upsampling. Even if the results provide better sharpness and well-recovered structures, this approach suffers from inconsistencies due to the independently optimized texels. In addition, discontinuities arise between adjacent tiles which are not optimized in the same loop, as illustrated with the red arrows. Indeed, optimizing for a full 4K SVBRDF requires to split the material into patches because of the limited amount of available video memory. Finally, direct SVBRDF optimization results in high-frequency noise in the maps. Our approach consists in using a small multilayer perceptron as a spatial regularization, which take as input a n by n tile of SVBRDF maps and output a 1 by 1 entry which is fed to the differentiable renderer. The rendering loss leverages the upsampled radiance mentioned before and now optimizes the weights of the MLP using backpropagation. This workflow has several advantages. It enforces spatial regularization, preserves the tileability of the input, and improves the upsampling speed, enabling 4x super resolution in a minute at 128 by 128 resolution. We now present results of our method for radiance-based upsampling of SVBRDF. Note how our methods provides well-defined geometry and exhibits less aliasing and overshooting artifacts compared to bilinear and Lanczos upsampling. Superresolution is a fundamentally ill-posed problem, and the amplification of the signals requires priors that are either derived from smoothness hypotheses or learned priors. Our approach takes a RGB radiance upsampler as metaparameter and offers options for supersampling SVBRDFs. Notice how the two results showcase different contrast, shapes, and colors when learned on 2 different upsamplers.